Well, good afternoon. Hope everybody's doing well. So today in DiffyQs, we're going to start where we're going now. Now we kind of talked about different methods of solving the second order differential equations. We're going to start using them. We're going to start looking at real life situations, scenarios that lead to second order differential equations that stay second order. I mean, if you kind of go back and think about what we did when we did, air resistance and we threw that in, technically it was a second order because you remember we had acceleration that was v double or x double prime, but we were able to make it just a first order by doing a little bit of a substitution, right? Where we let v be our variable. So then position or acceleration was a v prime. But we're going to look, starting today, we're going to look at examples where we have to have them as second order. And we're going to be able to put into play the techniques that we've built to solve them. And we're just going to apply them. So that's my plan. But as always, I like to open it up to you guys first. Is there anything that you guys would like to talk about? Any homework questions you're curious about or anything like that? All right, well, I'm not seeing any or hearing anything, so I will take that as things are going okay. Hopefully you've at least tried a few of the like reduction of order and stuff like that. Um, but as that comes, as you start playing with it, let me know if you have any questions. I imagine that once you get to variation of parameters, there might be a little bit more there. But it's all just procedure, right? It's all just process. It's all just monkey math, as I like to say. All right. Well, then I say we go ahead and dive in and start looking at real situations where we get second order differential equations that we can't just immediately reduce to first order. So I'm going to go ahead and share my whiteboard screen here. And let's just start with this as a thought. What I want to do is I want to look at a spring. And I want to look at a spring that's got just a mass attached to it. And we're even going to go into this hypothetical world of no friction, no drag, no resistive force. Okay, so this isn't quite real world yet. This is still kind of in that theoretical. But basically what we're going to do is we got this mass that's hanging off of a spring. And I want to be able to just pull it down and let it go. Now, you already know what's going to happen. I'm sure you've seen this bunches of times, but I pull that mass down and I let it go, and it's just going to start bouncing up and down. So let's actually look at it in terms of the forces that are actually applied to that mass. Okay, so let's not worry about the force that I'm going to put on it to pull it down. Okay, because that part, that's just going to get us going. All right, that's just going to get us going. But after I let it go, what forces are actually acting on it?
Gravity and then the spring itself.
Okay, so we've got the two. We've got gravity pulling it down, and then we've got the spring that's either pulling it down or sorry, either pulling it up or pushing it down, depending upon which side of things we're on, right? So let's put those arrows on here. So we got gravity. And then there's going to be a spring force. So let's just think that we've got it pulled downward. So maybe this was equilibrium. So this is where it would be if nothing else was going on. And so right now, what we would see is a spring force that's actually pulling it upward, right? Okay, so let's just start building the good old F equals ma business using Newton's laws, right? So we know that mass times acceleration is going to be the sum of all the forces, which in this case, we're going to have our gravity, which is just going to be mg. And then the spring force, obviously that's going the other direction, so we're going to put a minus. But how do you get spring force? Do you guys remember Hooke's law? What does the force do to a spring?
Don't we need the spring constant at least?
Yep, we definitely do need to know the spring constant.
And it was x times the spring constant.
Exactly. And thanks for throwing that in the chat box there, Ralph. It's going to be minus k times x. And in this case, the x, that's your displacement. So it's how far are we off of equilibrium? And then K is what we call the spring constant. So it's just a property of the spring. It basically tells you how easy it is to stretch or compress it. So like a slinky, those little toy springs, those things have a very small K because it's super easy to stretch or compress. But then like a spring that's part of a car shock, car I forget the word, suspension system. That's going to be a much larger K because it takes a lot for it to deform. All right, and so what we're going to do is we're going to go ahead and just keep this as minus kx, and that actually works perfectly even if it's on the other side of equilibrium, because you can imagine if we're now up here where we're compressed, now the spring is trying to push down, but our x's, if we think of this as 0 and x's are positive in this direction, then that's now a negative x, which makes this a positive amount. So it's pointing in the right direction. So it turns out that this is going to work for regardless of whether we're below or above equilibrium. We can just use minus kx. All right. Well, let's replace this a. We know that that is actually x double prime. And if I just kind of move things around a little bit, we get x double prime plus k over mx equals g. So I just move the kx over and then I divide it by m. But there it is, guys, staring right at you. Here is our linear second order non-homogeneous. So something just as simple, I mean, and this is simple, right? This is just, I've got a mass on a spring, I'm pulling it down, I'm letting it go, leads to a second order non-homogeneous linear differential equation. Okay, so let's solve this. Let's actually solve this with the K's and the M's and the G's and all that. Let's keep all those things in there. This way, we're good for any spring. We're good for any mass that's hanging off of it. If we leave the G, we're good for doing this on any celestial body. So you want to do this on Mars or the moon or whatever, it doesn't really matter. All right, so let's think about this in terms of how we solve it. So it's non-homogeneous, which means we need to start with solving the homogeneous. And so the homogeneous would be x double prime plus k over m times x equals 0. So think about how we do this. We make the polynomial. It's going to be an r squared plus k over m equals 0. There is no x double prime, or sorry, x single prime. So there's no r in this, no r term. So this actually is really fast. We get r is equal to plus or minus the square root of negative k over m. So this is going to be plus or minus the square root of k over m times I. So in this situation, we are actually getting to complex roots, right, to imaginary pieces. So what does that make our fundamental set? What form? Sorry, go ahead, whoever that was.
E to the lambda at t times cosine of omega t.
Okay, good. Yeah, so the in general, if we have, I didn't mean the plus or minus there just yet. When we have complex numbers, when it was lambda plus or minus omega times I, we got e to the lambda t cosine of omega t for one of them. And then the second one was e to the lambda t sine of omega t. Right, so that's in general. So if we look at ours specifically, what's lambda?
That's 0.
It's 0. So that means that e to the 0 piece goes away. And then omega is the square root of k over m. So we're going to get y1 is going to be cosine of the square root of k over m times t. And then y2 is going to be the sine of square root of k over m times t. All right, so there's our fundamental set. The homogeneous part, that's just this.
You know, it's funny. This already is starting to make sense with the whole spring because it's going to be, you know, it's going to be similar to an oscillation.
Yeah, not similar to. It's going to be exactly to.
It is, I suppose. Yeah.
And I don't know if you remember when you learned about springs, which I think was, well, I know we definitely talked about it in second quarter physics. For those of you who had physics with me last year, but you might have seen it other places. That square root of k over m should look really familiar because that has everything to do with the period and everything. Like that's a big deal.
Yeah, I remember the first time I was taught sine and cosine functions, even like in trigonometry back in high school. Like they used a spring as like an example of what sort of situation it would model.
Yep. And now you guys are sophisticated enough mathematically to see where it's coming from. Dude, how cool is that? Right? I mean, I know I overuse the words cool and get excited and stuff like that, but I know for me, and I know a lot of you are like me, for me, it really was incredible to me to finally get to the point where I was like, oh, now I understand. Now I understand when they just gave me these equations. Now I see where they come from. And it definitely gave me more understanding, and I really appreciated that. And so I was always happy once I got to a point, like if my math was lagging, right? There are plenty of situations where you guys already have the math in order to do stuff in physics. But when it is lagging, I always loved when I got to that point where it's like, oh, now I see it. Now I see why it had to be what we had and why we saw what we saw, right? But anyway, so there are those pieces. And then we still need to do one more thing, right? Because this is non-homogeneous. We actually have to get a solution to the homogeneous part. So to do that, we need to use one of our methods. So if you guys want to do undetermined coefficients where we make a guess? Do you want to do reduction of order where we put in one of the solutions that we have? Or do you want to do variation of parameters where we use these two and create the system of equations and then find our solution?
I prefer if we did order reduction.
Okay. So Jacob suggests using order reduction. Is that because you think it's going to be easiest or because you want to see it again to remind yourself how to do it?
I want to see it again.
Okay. What do the rest of you guys think?
I mean, I was thinking just making a guess since it's equal to a constant.
Mm-hmm.
Yeah, I'm with Bradley.
Okay. Well, Jacob, I think you've just been outvoted 2-1. This is one now, and here's where I'm going to go. Like, I appreciate your thought about seeing reduction of order, and I'll tell you what. If I don't remember to do one later today with reduction of order, remind me on Friday, like at the start of class, and we'll kind of go and do one with the reduction of order. But if you think about this like a mathematician would think, right? What's a mathematician going to do? Well, they're going to do the thing that's easiest. And this one, just like Bradley said, since this is just a constant, you totally want to go with making your guess because your guess is going to be super easy. The form that we're going to want for our particular, it's just a constant, right? Because a constant, I guess it should be x particular. All those things should be x's because we're doing x's, not y's. Sorry. But anyway, so this is a polynomial of degree 0. So we're going to guess a generic polynomial of degree 0. Right, talk about easy, because the second derivative, of course, is 0. So if you fire that in here, you get Ka over m equals g, or A equals mg over k. So there's our particular solution to this one is just mg over k.
That really looks familiar.
Crazy, right? Crazy, crazy, crazy. So now we can put all that stuff together. And here's our solution. We got x is equal to mg over k plus c1 cosine square root of k over m times t plus c2 sine of square root over m times t. And again, we would actually get the c1 and the c2 by using our initial conditions, right? I pull it down 10 centimeters and I let it go. Okay, so my initial position is x of 0 is 10 or 0.1. Let's go metric. So 0.1. And then my x prime of 0 is 0 because I'm just letting it go. Or I'm moving it up 5 centimeters and then I'm pushing it down with a certain force or a certain velocity. Okay, well then there's our different initial system or conditions and blah, blah, blah. But there it is, guys. There is the answer to every single spring problem. Like every single one of them. That's going to be the position of your mass. Again, C1 and C2 are going to be determined by how we start this off. But in the absence of any kind of frictional forces, this is what we get. All right, so you're starting to see a lot of things that came about in the spring world. So, like I said, the square root of k over m, or then when I wrote mg over k, and Bradley's like, ooh, I recognize that. We start seeing it. Now, this whole mg over k, that's really just the offset due to the mass. Like think about mg. Mg is your gravitational force. When you divide it by k, like if you just ignored all of the cosine stuff and you just looked at this piece right here, that's saying mg equals kx. That's saying your gravity is equal to your spring force. This is what's necessary for your offset. And since that's really just on the graph, that's just a vertical shift, that's why we never actually had to worry about that. Like, think back to when you did labs with springs. And you were always only concerned with distance away from equilibrium. After you'd put on the mass, you didn't care what it was like at the beginning. And that's why. All that does is just shifts it down, so or up, right? And so everything's shifted that same amount. That doesn't change anything else, right? All of the action is with the other stuff. So let's take a quick look at this other stuff, though, for a second, because we've got a cosine plus a sine. Well, you know that there's an identity for that. And there's, no matter what our trig is, you know that there's always going to be an identity that we can use to help us, simplify stuff down. So let's look at what trig says we can do with that. So first things first, I'm just going to make life a little bit easier by calling that square root of k over m omega. Okay, so that way we don't have to keep writing square root of k over m. We all know what it means. I'm just going to go ahead and call that omega. So let me actually, I don't want to clear the whole thing. I'm just going to do some erasing. So give me a second here. I don't really need the picture, any of this stuff anymore. There's that. We'll keep our equation just in case. But let's just clear all that stuff. Okay. So I'm going to ignore the mg over k, because again, that's just a vertical shift. Instead, let's just look at these pieces. So we're going to go ahead and call omega. We'll make this omega. So we get, let's look at C1 cosine of omega t plus C2 sine of omega t. And so I want to go ahead and try to combine those things. All right, well, you can use the identity for the difference of angles for cosine. And what we can do is actually call these C1s something in terms of some sort of a shift. Basically, this is the substitution we're going to do. We're going to let C1 equal, I'm going to call it big R, times the cosine of phi. Cosine of phi? Yeah, cosine of phi. And then C2 is going to be big R sine of phi. And the reason I'm choosing this is basically I'm making a little right triangle here where I've got phi. And I'm going to make this guy big R. So I'm kind of like thinking about that C1 as kind of a horizontal piece and the C2 as a, whatever. This is sort of how this is going. Don't worry about the fact that it's horizontal or vertical. But if I define it this way, then I get that R is equal to the square root of C1 squared plus C2 squared. So just go with me for a second, okay? So if we define it this way, then that means we're going to have R times cosine of omega t cosine of phi plus R sine of omega t sine of phi So I just plugged in the C1 and the C2. I can pull out the R, and then if you look at this other piece, that's actually from the difference of angles for cosine. That's the same as the cosine of omega t minus phi. All right, so with just this little fiddling around, which is totally legit, I can do this however I want. But I want you to notice what happened. I put these two things together and I got a single trig function. So when you have a sum of sine and cosine that have the same frequency, you end up getting one trig function. Now, it's kind of good that this happened mathematically, because this is what happens in the real world. I pull that spring down and I let it go. It's just going to oscillate back and forth nice and regularly. It's going to be sinusoidal. So it's exactly this. So in the absence of any kind of resistance, this is the form that we get. Now R, that actually holds the C1 and the C2. And so does phi, right, in a manner of speaking. But think about what that phi is. That phi is just an offset. And that should totally make sense, because think about where phi is coming from. It's coming from the C1 and the C2. Well, C1 and C2 are coming from your initial conditions. So depending upon your initial conditions, you're going to end up starting at a different part of the oscillation cycle. Duh. Okay, so mathematically, this is awesome. It does exactly what we expect it to do. It's exactly what we want it to do. It gives us something that's just trig oscillation. All right, so cool, makes sense. Kind of see it, I hope. All right.
I'm curious as to why we are allowed to get away with saying that. Oh no, never mind. I just answered my own question. I was going to say, how can we say that C1 and C2 are equal to R, but the trig function takes care of that since they're different?
Right.
Got it.
Yep. That's exactly it. And it's just one of those, like that. Think about what we did. In essence, we converted it to polar. Really, if you think about it, with the big R and the cosine of phi and all that, we converted it to polar. We do that shit all the time, right? So that was just good old polar conversion. So if you ever end up with one of these things, you can always actually figure out what the amplitude of the resulting wave is. It's going to be that R. So the square root of C1 squared plus C2 squared. And you're also going to know whatever that phase angle is. You can just use inverse cosine or inverse sine for either one of those, right? You put in for the R, the square root of C1 squared plus C2 squared. And so for either the first or the second substitution, you can find out that phase angle, and then you know exactly what's going on. Okay, so
to solve for this R
Uh-huh.
in a initial value problem, we wouldn't need two pieces of information, would we? Since there's only one constant now?
No, you still would need two. Well, yes and no. You still need two pieces of information because there's still two unknowns. What are the two unknowns now? Instead of, if you don't want to call them C1 and C2, what are the unknowns now? One of them is R.
Phi, I guess.
The other one is phi. because we
That's
don't
crazy
know that.
that they don't get lost, or they don't
Yeah.
go away.
Yep. So we still need, and like to actually find the R and the phi, like for R, we'd need to know those two C's. And you would also need that to find your phi with either one of these, right? You know your R and then either C1 or C2. So I know it's still two pieces of information that you don't know. It's just, you'll get one of them. Well, you'll get them in different ways because your initial conditions are never about R and phi. They just aren't. What your initial conditions are always about are your X and your X prime, which leads you to your C1 and your C2. You know what I mean? So, but regardless, yeah, you still have the two pieces of information that you still have to find. Yeah, it's still a second order. There is no magical, we can just ignore it now. We just have renamed it. Right? Again, think back to polar. Was it sufficient just to know the X coordinate of a point to get the R and the theta?
No.
You needed both. So it's the same kind of a deal. All right. Well, anyway, there you go. It doesn't matter. You've just solved, we as a group have just solved every single spring problem where there's no resistance. And that's a big qualifier. And obviously, you know where we're going to go, right? After we get done with this, we're going to go to, well, what if there is resistance? And we'll see that it does what we want it to do. All right, now, because this mg over k business doesn't matter, what we'll often do, just because it makes life easier, is we'll just rewrite this equation as x double prime plus x over m, or k over m times x, equals 0. Because think about what's the only difference in the solution to this differential equation. Well, oops, sorry about that. I was trying to drag something off my screen and I drew a line. That's just going to make this go away. The mg over k, that was the only bit that actually came from it being non-homogeneous. And since that's just a scalar, it's just a constant, like we said, it's just a shift, we're just going to completely ignore it. So it's pretty common, and so common that I'm going to do this. I'm just going to completely forget about that G. I don't really care. Like, yes, I know gravity affects this, but all it does is shift everything down. So you'll see this a lot in the homework problems or when you're reading books about this. They'll always talk about getting equations for position relative to equilibrium. And then you don't actually have to care how much the spring really got stretched or compressed because it doesn't matter. All right. Anyway, so that's the first thing, is just realize that we often just make that equal to 0 and then it simplifies this down, right? Or more to the point, makes it so that this is our equation. All right, now, what if though it's non-homogeneous, but not just because of gravity? So let's change our perspective on this a little bit to, let's make this so that it's not equal to 0 and it's not equal to G, but it's actually equal to something else. All right, and I'm just going to call it for right now just f of x. And this guy is very often called a forcing function because it's going to be something else that's sort of driving the motion. For example, what if we had this spring set up, but we put a fan underneath it that was blowing upward? Now we're applying another force, and that's going to cause different motion.
Oh, at a medium count too?
Okay, so the medium actually won't account for anything yet because we haven't put in any kind of a drag factor. We call that damped motion. So this is going to still be undamped motion. But this could be things like, all right, let's say we've got that mass on the spring, but the base of the apparatus is on a table that's bouncing up and down. That's obviously going to cause different motion up here. Or, all right, so we're not really looking at changes in the medium. We're looking at, or the medium itself causing an issue. We're just talking about there's some other force that's being applied to the entire system. That's the forcing function. So when it comes time to solve this, think about what that's going to change. What's going to change in our process as soon as we put something else over there?
The way we solve it or find our particular function could be different.
Yeah, and that's actually the only difference. Because all of this stuff, the homogeneous part is still the homogeneous part. So we're still going to get this every time. It doesn't matter what that forcing function is. What will change is our particular. So it might change how we have to solve for it, right? Like we might not be able to make a guess for it. We might have to do reduction of order or variation of parameters or something like that. But there's something even kind of more potentially a problem with this forcing function for this specific scenario. Can you guys see what might be an issue with this thing? Or I should I wrote X, that should be T. I'm thinking of a specific type of forcing function that's going to be maybe a problem.
My thought is if it's another force, well, that's another mass times acceleration, right?
Well, it gets incorporated into the mass times acceleration. So it really doesn't change anything. And this equation is still this equation. But I'm looking for a specific function, specific type of function that's going to be an issue. And to help even push you in that direction, think about undetermined coefficients. Think about when we make a guess. What was the weird outlier when we made a guess?
If we got repeating functions, like
Okay, yeah. So if our homogeneous part was part of the non-homogeneous guess, so you can see that for this one, since our guess ends up being, or our homogeneous ends up being some sort of a cosine sine thing, there's going to be a potential issue. Really, the only time we have to worry about this is, I'm going to say we got to watch out for things of the form sine of omega t or cosine of omega t. So other than that, you apply any other force, no big deal. You just go through whatever method you have to solve it. But if you've got a driving function, a forcing function that's sinusoidal, we definitely have to watch out for it. And I'm just going to even add to this that there are still some interesting things happening even if the omega isn't the same. So I'm just going to put that in a little box here. So even if this omega that we find right there, or that's part of the forcing function, even if it's not the same omega as in our homogeneous set, we still get some interesting things happening. And let me show you why. All right, so let's just start with the what happens if it's exactly the same. All right, so what if we've got a forcing function that's got the same frequency as our homogeneous set? So let's think about what the solution then is going to look like. Let me actually erase over here. So if we were to put that in, we're going to get x is equal to, there's going to be some sort of a t cosine of square root of k over mt plus bt sine square root of k over mt plus the C1 and C2 stuff. All right, so the first two parts, those are, these two guys were from our particular, and then these two are from our homogeneous. There should, hold on, there should not be a T on this piece. This should just be C2 sine. All right, now I want you to think what this is going to look like. We already know that the second part, that this part is just a oscillation, right? What are we going to get from the first part? What happens when we multiply by t? Think just graphing it. What would that do?
It will be like that wave, but going up with t.
Exactly. Think about the line y equals t or y equals x. So boom, boom. Because you can factor out that t. So that t actually now acts as an amplitude envelope. And what you're going to see is this sort of thing. So you're going to see that sine wave actually growing in strength. So that's what happens when we're in this, if our forcing function has the exact same period or frequency as the fundamental set, we are going to get this so that the actual amplitude of that resulting oscillation just gets bigger and bigger and bigger and bigger and bigger and bigger and bigger. All right. This is potentially a problem. Because let's just think about this as, let's say we had something physical that was making this wave. Let's think about like a building and an earthquake happens. So the building starts shaking. Actually, I'm gonna.
Real quick, there's been a lot of those recently.
Earthquakes?
Yeah,
Yeah, there have been.
kind of weird. Wonder why.
Sometimes people will say that That's because there's a sign of something bigger coming. I think a lot of times the reason you get strings of earthquakes is just think about it, like you got some plates that are kind of rigid, stuck together, and one slips a little bit. It's kind of like when you've got kinetic friction versus static friction, right? If things are already moving, friction is less. And I kind of think that that's what happens here, is that you get a little bit of a jolt, which, oh, okay, now it's a little bit easier to slide a bit until it gets itself wedged again. So, but I am purely a recreational earth scientist, if you know what I mean. So don't quote me on that. But anyway, so think about this. So you got a building, and let's say an earthquake happens, right? So it starts to shake. It gets that kind of oscillation that we expect instead of a vertical spring. Okay, so this is horizontal. Okay, so let's just say there's just the one real quick shake. Okay, it's gonna eventually die out because of air resistance and all that we haven't talked about yet. But even if there wasn't air resistance, think about what would happen. Okay, so you get that shake, it just starts oscillating, but it just starts same oscillation back and forth. That would be pretty crazy to have a building that's just like always shaking. But okay, but now think about the same thing. So the amplitude of that shake is how far the top's moving of the building, right? Like that's the amplitude of our graph. So now let's say we've got this situation where there is a forcing function that's going to cause this thing to shake, but that forcing function is coming in at the same frequency. Okay, so now earthquake happens, it starts shaking, but it continues, the ground continues to shake at the same frequency. If it's the same frequency as the solution to the homogeneous, the top of that building is going to start doing that, right? Small oscillations, they get bigger and bigger and bigger. And you can see why that might be a problem, right? What's going to happen? Well, that building is going to collapse because it was too much. All right. This effect is called resonance. I don't know if you've heard of that term, but this is resonance, where you there's sort of a natural frequency. The natural frequency was that square root of K over M in the case of the spring. So like every spring has a natural, spring mass system has a natural frequency for it. Everything that can oscillate has its own natural frequency. Think about when you, with standing waves, sound waves, and you've got like a pipe, like in an organ, there is a natural frequency for that. If you were to produce the same frequency as that natural frequency, you're going to get resonance, and it's just going to make that thing build and build and build and build. It's going to get louder and louder and louder. A really good example is the Tacoma Narrows Bridge. Good old Galloping Gertie. And I bet you money you have seen this, but we're going to go ahead and find it ourselves. Let me share my screen here. We'll go find a video of it. Computer. There you are. My computer is arguing with me. Okay, so we're go to YouTube. Oh, by the way, this is, you guys all know all the videos or the video repository. But let's look up here, Tacoma Narrows Bridge. Oh, look at that. First ones. And this guy's pretty classic.
Sorry, I left a gentleman alone in my apartment, so I'm tracking him to make sure he leaves.
So real quick question. Did you guys hear sound?
Yeah.
Yeah. Okay. Well, I just muted it because we don't need to see it. But anyway, so this is a bridge that was, and keyword is was, in Washington State, just outside of the city of Tacoma, and it goes over a body of water called the Tacoma Narrows. but you'll notice that it's just oscillating back and forth here. This is harmonic motion, right? I mean, it's the same thing that we were talking about. But what's kind of crazy about this one is that it starts building. It starts getting bigger and bigger and bigger, because there is a natural resonance, a natural frequency to this, that was being met by the wind. And the wind was driving this oscillation and making it so that the amplitude got more and more and more, meaning that thing is going higher and lower and higher and lower until eventually the bridge couldn't withstand the stress anymore and ended up collapsing. So we got to watch until it collapses, because otherwise I'm just teasing you guys.
It's incredible how bendy it is.
Yeah, but check this out. I love this image. So that's the cables that are going into the bridge, and you can actually see how much shaking is going on that thing. Like, I don't know if you guys have ever been on like the Golden Gate Bridge or anything. Those cables are huge, right? I mean, they're like really big around. Yeah. Oh, so they're gonna go try to rescue the dog. If I recall correctly, the dog like bit the guy, and so he was like, "Okay, never mind. Screw you." But yeah. All right. Oh, here we go. We'll just speed it up a little bit. But now you can really see. I mean, look at how much that's moving now. Until eventually, oh, here it comes. Spoiler alert, it's going to collapse. Crunch. All right. So for those of you who are thinking about being structural engineers, this is something you definitely have to pay attention to. You have to look and see, are we designing these structures, these buildings, these bridges, so that they have some sort of natural frequency that is likely to show up? Because everything's going to have a natural frequency, but the goal is to design it so that it's not one that's going to show up from other things. Another really good example of this was Mexico City. This is long before you guys were born, because it was back in the 80s. There was a big earthquake in Mexico City, like a really big one that destroyed like so much of that city. And it was kind of the same issue. Mexico City is actually built on an old lake, and so the sediment is really, it's kind of like jelly, like Jello. It's sand, but kind of still a little bit watery, you know. So anyway, so this earthquake, what ended up happening was it shook, like, think about Mexico City being on a bowl. It shook that bowl, and then the wave kept bouncing back and forth in that bowl, and that ended up matching natural frequencies of a lot of buildings and caused them to do that until they collapsed. So anyway, this is a real consequence of these second order differential equations, right? So when you actually match the frequency, it leads to a t times that sine or cosine, which then just causes that amplitude just to grow and grow and grow, which mathematically, yeah, cool, whatever. Physically, it's a problem. That's when your bridges collapse.
Theoretically, would it be possible for gravitational waves to match the frequency of a planet?
Maybe, I don't know. I honestly don't know enough about gravitational waves. But what I will tell you though is that you would need those gravitational waves to not just be like one that passed through. There would have to be a series that just like kept going and kept driving the motion. So if you could get kind of the equivalent of what I was talking about with like Mexico City, where you could have a gravitational wave that just sort of keeps going back and forth past some sort of celestial object, then I would say, yeah, conceivably, yeah, it's possible. But I really have no idea what those numbers would be, like, or if they
It's
match up.
yeah, it's probably so astronomically unlikely.
Yeah. There are other places where you see it in, well, in the fluid world, in oceanography, you have these things that are called, excuse me, seiches. It's spelled Seiche, I think, if I remember correctly. Just put it in the chat box. But a seiche, this will happen in like a harbor where you've got waves that are coming very regularly. So there's a forcing function that's sinusoidal. And if that actually meets the same frequency as the natural frequency of the basin of the, the harbor channel, where everything is, you'll get the setup where that wave starts going back and forth and building in that harbor. And so you can just imagine now, if you've got boats and stuff in that harbor, now they're getting sloshed up onto the shore and stuff is getting destroyed. So this will happen with as a byproduct often of tsunamis. It's not the tsunami itself that's the problem, but the tsunami has the right frequency that it matches the natural frequency in a harbor and causes everything to go out. You can kind of see the same thing in a bathtub. I don't recommend doing this in a bathtub because it'll get water everywhere. But like if you're sitting in a bathtub and you just start, kind of rocking back and forth, you can rock back and forth, not even very hard. If you find the right frequency, it will make the water start sloshing higher and higher and higher. That's another really good example of where you can see this. You can create it yourself. But I do not advise this. Whoever you live with, if you do this and they get mad at you, don't say, hey, my physics professor, my math professor said that this is something I should do. That's not what I'm saying. I'm just saying this is a place where it happens. But anyway, it's a real thing. And you can see mathematically why it's a thing, because the frequency matches, and we already know solving these equations, that means we got to multiply by a t. Now, I told you that you still get interesting stuff, even if that frequency isn't quite the same. Let me show you what I mean there. And this is going to bring back something else that we talked about in physics for those of you who are in Physics 108, I think it is. Let me just erase some of this stuff. I'm going to erase this bit. No, we've already talked about it. But let's go to the frequencies aren't quite the same. All right, so I guess we don't actually even need our forcing function anymore. But let's do this. Let's say we're going to have our natural frequency. I'm going to call that omega naught. Okay, so we'll let omega naught, this is going to be the natural frequency. I just want to make sure, because I've been bouncing around. You guys see the whiteboard now?
Yeah.
Yeah, okay, thank you. All right, so this is going to be that natural frequency, the square root of k over m thing. Okay, so we'll call that omega naught. Let's say that we've got some other function or some other omega in our forcing function. And just for the sake, I'm just going to call it regular omega t, where it's not omega naught. So our solution then, if we kind of were to build it like we've done before, we'd see our x is going to equal some a cosine of omega t plus b sine of omega t, because that's going to be our guess for this form. And then, of course, that's going to add on to the c1 cosine of omega naught t plus C2 sine of omega naught t. Okay, well, remember how we were able to kind of combine two trig functions into one? You can do exactly the same thing here and combine these set of 4 functions into some others using some trig identities. And what you end up getting when you do this is a product of 2 trig functions. And the resulting function looks something like this. Where if we look at the motion, we're going to see oscillation that builds and then gets smaller and then builds and then gets smaller and then builds and smaller and so on. And this building and getting smaller is very regular and actually follows another sinusoidal piece. If this looks familiar, it should, because we've run into this in lots of different places in math and physics. But specifically, if we look at where we've seen this in physics, it was with what we call beats. Do you remember that term? Maybe, hopefully. So these are called beats. And so there's actually like 2 frequencies to this. There's the kind of underlying frequency of the blue, and then there's the frequency of this green oscillation, and that's the beat frequency. And we saw this in physics when you had 2 sounds that were really, really close to the same frequency. And if you play them together, what you hear kind of underlying is sort of a pulsing wah, 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 wah. I don't know if you guys remember this that were in my class last year, but if that frequency is not the same as natural frequency, but close, you get this. And in fact, the closer those frequencies are, the smaller that beat frequency is. So the 2 frequencies, because the beat frequency is the difference in the 2. Let me actually just write that down here. And I'm just going to make it the absolute value. So that's always positive. So if the frequencies are really far apart, that beat frequency becomes so large that you don't notice it. But if they get close enough, you can actually notice that change in frequency. And this is how people tune instruments. When you're listening to try to tune an instrument, if you're really good at this, you will notice it's out of tune because you'll hear the beats. And so you adjust the tuning until all those beats go away. But this is by far the most interesting thing when we've got this kind of oscillatory motion, is when the driving function is also oscillatory. Specifically when it's the same, because then you get this crazy unbridled building of the function. But even if it's close, you can get something kind of funky going on. Other than that, I mean, if it's exponential, okay, so you got exponential with a little bit of bounce to it. Polynomial, okay, it's a polynomial with a little bit of bounce to it, whatever. But it's also when that function is bouncy that you get some interesting things happening. All right, so cool for that. Kind of see what's going on. All right, so now let's add in some drag. Let's add in a resistive force. So now we're going to do the same situation where we got the spring with the mass. So we still have the 2 forces that we talked about before. We've got gravity, and we've also got spring force. But now let's add in a resistive force. So this is drag. This is air resistance. It's whatever you want to call it. And we're going to do similarly to what we did when we were talking about just air resistance. We're going to make this so that it's proportional to the velocity, because that seems to make good sense. The faster you go, the more resistive force you're going to get. All right, so let's build this thing again. Let's build the differential equation, and let's see what that's going to have to look like when we do Newton's laws. Okay, so how's this change now?
A third force has been added. Or
Okay, so we're going to have a third force that we're going to be combining on there, but now it's going to be a drag force. So, and we need a constant of proportionality. I'm not going to use K anymore. I know we tend to use that as our constant of proportionality, but we need to restrict that or reserve that for spring. So it's kind of standard to use gamma when we're having this conversation. But here's basically how this is going to work. So we're going to have our sum of forces. Well, it's going to equal gravity. So mg plus some sort of a, oh, not plus, minus some sort of force that's proportional to velocity. So that's going to be our drag. And then minus kx. So this is spring. This is drag. No. First one is not spring. First one is gravity. Try that again. All right, so gravity, and then minus drag and minus spring. And drag is always going to be in the opposite direction, so it's always going to be negative. All right, well, do the same thing. That this is mass times acceleration. So if we move things around, we get mass times acceleration plus gamma times v plus k times x equals mg. Now, from the same argument as before, I'm going to ignore the mg. I'm just going to call it 0. And we're just going to base everything off of the new equilibrium once the spring is on there. All right, well, check it out. This is now mx double prime plus gamma x prime plus kx equals 0, because velocity is the derivative position, acceleration is the second derivative. And again, we get a linear second order. This time it's homogeneous. But I'm going to go ahead and add this on here too, with constant coefficients. Because m, gamma, and k are all going to be constants. The mass is the mass of this object. The spring constant is the spring constant, and this gamma, well, that gamma, it's going to be dependent upon the medium. So remember earlier when I was talking about this and Bradley brought up something about the medium. Now, that's what gamma is going to do. This is going to depend on the medium. And basically the way to think about this is bigger gamma equals more drag. / resistance. Okay, so if we've got a bigger gamma, that just means there's going to be more drag and more resistance. So, for example, if we had this spring and mass system in water, that's going to be a bigger gamma than if it's in air, right? The water is going to slow down this motion faster than the air will. Or if it was in motor oil, or it was in honey, or it was in insert favorite fluid here, each of those fluids is going to give you a different gamma. All right, so that's really going to come from just what the material is. And if you were going to like be doing something experimentally, like let's say you were really trying to do some sort of oscillation in the air, you would just do a couple of, real quick experiments to see how much force you were losing with given velocities, and then you could use that to actually find your gamma for that material. All right, so if those guys are all nice and constants, we know exactly what to do with this. Again, we're going to make our polynomial. It's going to be mr squared plus gamma r plus k equals 0, and we're going to solve this. Now, if we were to do this generically, we'd have to use the quadratic formula. So it would look like this. So negative gamma plus or minus the square root of gamma squared minus 4mk over 2m. What I want to do is think about the three different possibilities that can happen. Because as we've seen with anything of this form, one of three things happens. We either get two distinct real roots, we get one real root that's repeated, or we get two complex roots. So let's think about what the different forms are going to be, or what we're going to need to get those different forms. All right, well, let's go with the first case. And the first case, let's call that two real roots. Okay, so case number one. All right, so first of all, in order to get two real roots, we need gamma squared minus 4mk to be positive. Do you see why?
You said gamma, that whole thing needs to be positive?
Yeah.
Oh, because then we will get real roots.
Yeah, because then we get a square root of a positive number. Those are real. Okay, so we get our two real roots when this happens. When this happens, what our solution is going to look like, we're going to get x equals e to the minus gamma plus square root of gamma squared minus 4m. You know, the problem is I'm trying to write too small here. Minus 4mk all over 2m t, and then you C1 plus C2 e to the minus gamma minus square root of gamma squared minus 4mk over 2m t. So that's case number one. Now, obviously, what these exponents are going to look like are going to change with the gammas and all that. But what I would like to talk about is what's the long-term effect of this? What happens as t goes to infinity? So really, that's the question of, since they're exponential, these multipliers, are they positive or negative? Now, this second one you can see pretty clearly is going to be negative because we have negative gamma. We're subtracting more stuff, so that's more negative. Dividing by a positive gives us a negative number. So that second one definitely goes to 0. What about the first one?
It
Well, this one-
depends. Yeah, it depends on whether or not the square root stuff is larger positively than gamma.
Okay, and that's exactly right, Bradley. We got to look at this square root thing. So let's just kind of follow. So we've got gamma squared, and we're going to take something away. So what's inside is less than gamma squared. Well, when you take a square root of that, that's going to be less than gamma. Right? Like let's say it was 4 squared. So if we had, say, 15, the square root of 15 is less than 4. So it turns out that this guy in the square root, when you take the square root of it, it's actually going to be less than gamma. How much less than gamma? Well, that kind of depends. But it's going to be less than gamma because this is always, we're removing something. All right, well, if we're going to take negative gamma and add something less than gamma, it turns out that's negative as well. So in this situation, when you have 2 real roots, this is your solution, and the trend as t goes to infinity is 0. So it will die out. So we get it, we let it go. It's eventually going to return to equilibrium as time goes on.
Good, it should.
Yeah, yes. We should expect that it definitely does that. All right, so there's case number 1. So let's go to case number 2. And let's do it this, the one repeated root. And this is going to happen when gamma squared equals 4mk. Because if gamma squared equals 4mk, then that square root is 0. And we're good. And so what we're going to get in this case is C1 e to the minus gamma over 2mt. Because that's our one and only root is minus gamma over 2m. And then the other piece gets a t times e to the minus gamma over 2mt. All right, so that's what we get in this situation. Now let's do the same thing. Let's look at what happens as t goes to infinity. The first part, again, clearly it's a negative exponential, so that'll go to 0. This one, we've got that negative exponential times t, which means we've got infinity times 0. And infinity times 0 is an indeterminate form, so we'd have to use L'Hopital's rule. But by now, I hope you guys realize that exponential stuff overwhelms polynomials. So long term, it's the exponent that's going to drive this, which also sends this to 0. So we actually get the same thing happening, is that it will eventually die out to 0. But it looks very different. Because this t times an exponential, yeah, that does different things. Like you draw a graph of that, it's not going to look exactly the same. But the long term is same thing happens. All right, well, let's go take care of case number 3. And of course, we know what's going to happen there. If we get to the imaginary or complex roots, we know we're going to get some sine and cosine stuff. But let's actually work it out. So here's going to be case number 3. And this is where we get the 2 complex. Now, this, of course, is going to happen when gamma squared minus 4mk is less than 0. So this gamma squared minus 4mk kind of matters a lot in terms of what it's going to look like, right? If it's greater than 0, equal to 0, or less than 0. All right, well, in this case, what we're going to get C1. Well, hold on. We're going to get e to the minus gamma over 2mt times C1 cosine of square root of gamma squared minus 4mk over 2m times t plus C2. Oh, actually, damn it. That's negative, so I got to reverse that. Hold on. Square root of 4mk minus gamma squared. There we go. And then C2 sine of the same thing, square root of 4mk minus gamma squared over 2m times t.
Why did you swap it inside the radical?
Because since it's negative, that's going to lead to an I, and the omega is the real part times I. So I needed to make it real. So I had to change that from a minus to a plus on the inside.
Got it.
I factor out the -1 that became the I, basically. All right, so there's the third case. And this one looks completely different. But if we, again, look at a limit as t goes to infinity, it's also going to equal 0 because the cosine sign is going to be oscillating, but it's being multiplied by this exponential piece that's a negative exponential. So that just brings it down. So in all of these 3 situations, as soon as we add drag, as soon as we add some sort of resistive force, we get motion that terminates. And we didn't see that with the other, right? When there was no resistive force, the motion didn't terminate. It just kept oscillating forever. All right, well, this should make you happier for those of you that are, real worldists, where you want to be able to match what's going on in the real world, because this is what we see, right? Like if I graph that first one, you're going to get something like, maybe not exactly, but something like this. So you're going to get your oscillation that's coming from the sine and the cosine. But then there's going to be some oscillation here, or a decrease on your amplitude that is according to the exponential piece. And that's what you normally see. Like if we did this, if we just took a spring on a mass, or a mass on a spring, and we just pull it down and let it go, we're going to see it oscillate, but eventually the oscillation gets short and then it stops. So like that's what that one looks like. The orange one, what you'll see with the orange one is something more like, let's kind of start it at the same place. You'll see something that's more like it starts to oscillate, but then it just dies out. All right, it doesn't actually oscillate. There is no sine and cosine, but this is first bit with the t times, it helps drive it up a bit, but then it just dies off. Well, think about the difference here. We've made gamma minus 4mk a little bit bigger. So that gamma, in essence, has increased. There's more resistance. There's so much more resistance that it's not going to let it oscillate. It's that point where it won't be allowed to go beyond the equilibrium. Now, if we go to the third case, this one, that's just a sum of exponentials. We've increased gamma even more. So imagine we're now like a thicker medium. And this is going to be one that just really just drops it down, just drives it down exponentially. Where it's just so resistive, it just pulls it back down. All right, so really in the physical world, what's going on here that leads to our three different cases is gamma. Because if we just assume m and k are constant, so we're looking at the same system, we're just putting it in different media, so only gamma is changing. It's the changing gamma that drives which of these three forms you get. The smaller gamma is, the less resistance there is, the more likelihood there is of getting something that oscillates. But if we make resistance big enough, eventually oscillation gets off the table and we're into one of these two scenarios. So we have names for all these because all of this is what we call damped motion. This first one, or I guess case 3, this is what we call underdamped. And you can see why it's called underdamped, because it's sort of like there is some dampening going on, but not a lot. The case 2, the orange one, we call this critically damped. And again, I think you can probably see why we call that critically damped, because it's the I was going to call it equilibrium. I don't like that. Well, okay, so it's the place where we transition from one to the other, right? So critically damped is where we're no longer going to get the oscillation. Okay, so then I bet you can guess what we call the third one. If this one was underdamped.
Overdamped?
Hey, there it is. Someone's thinking like a mathematician. All right, so then this one is overdamped. All right, so those are just the terms. So when you run into those, you know what we're talking about. All right, I think this is a good place to stop. I know we have a little bit of time left, but we'll go ahead and call this good for today. We'll pick up with this next time. We'll actually do some examples, and we'll look at what we get when it's damped versus undamped motion. What happens when we have different kind of forcing and all that. Because I know that like today we didn't really do any examples. We just ran through the math of it all. So on Friday, yeah, this is Wednesday. On Friday, we will do some examples. We'll actually look at what happens when we apply this, and it'll kind of back up what you're seeing with the math. But notice that this is like real application of second order differential equations, and pretty much physics, you get second order all the time when you're dealing with forces, because force is mass times acceleration. Sometimes it can get simplified down to a first order by doing like the trick we did with air resistance, but more often than not, it's something like this. And good old harmonic motion is one that we experience a lot. We see it a lot. And so you can kind of see where it comes from. Anyway, so with that, I think I'm going to go ahead and stop the recording, and I'll see everybody on Wednesday.